Sustainable engineering represents a fundamental shift in our approach to infrastructure and development. It is a holistic discipline that integrates environmental, social, and economic considerations into every project. This methodology goes beyond mere functionality and cost, aiming to create solutions that serve present needs without compromising future generations. Core to sustainable engineering is the prioritization of well-being across multiple dimensions. It focuses equally on environmental health, social equity, and economic viability, ensuring a balanced and enduring impact. This moves us far beyond traditional engineering practices, which often focus predominantly on immediate efficiency and technical performance. Historically, engineering primarily sought to solve immediate problems with a focus on functionality and cost-effectiveness. Sustainable engineering, however, expands this vision. It challenges engineers to consider the broader ecological and societal consequences of their work, recognizing that long-term success is intertwined with planetary health. The long-term impact of any project is a central concern. Sustainable engineering meticulously accounts for the effects on the planet and its inhabitants throughout a project's entire lifespan. This foresight is critical for preventing unforeseen negative externalities and ensuring enduring benefits for all. A comprehensive life cycle perspective is essential for sustainable projects. This approach scrutinizes every stage, from initial concept planning and material sourcing to construction, operation, maintenance, and eventual decommissioning. Each phase is optimized for minimal impact and maximum positive contribution. Ultimately, sustainable engineering pursues a dual objective. It strives to minimize the negative environmental and social consequences associated with engineered solutions. Concurrently, it seeks to maximize the positive contributions projects can make to community well-being and ecological integrity. Environmental sustainability forms a crucial pillar of this engineering philosophy. Its primary emphasis lies in dramatically minimizing the consumption of raw materials, energy, and water throughout a project's life cycle. This proactive approach conserves vital planetary resources. Material strategies are integral to this effort, promoting the utilization of recycled content and renewable resources whenever possible. Engineers seek out innovative alternatives that reduce reliance on virgin materials and minimize waste generation. The goal is to close resource loops and foster a circular economy. Energy strategies focus on designing systems that are inherently energy efficient and increasingly reliant on clean sources. This includes optimizing building envelopes, integrating smart control systems, and deploying renewable energy technologies like solar and wind power. Reducing operational energy demand is paramount. Water strategies involve implementing advanced conservation techniques and efficient water management systems. This ranges from rainwater harvesting and greywater recycling to optimizing irrigation and industrial processes. The aim is to minimize freshwater consumption and protect precious aquatic ecosystems. The overarching goal is to significantly reduce the environmental footprint of all engineering projects. This means designing with nature rather than against it, to create structures and systems that exist in harmony with their surroundings. Every decision considers ecological integrity. Furthermore, environmental sustainability focuses on impact mitigation. This includes reducing pollution of air, water, and soil, as well as minimizing habitat destruction. Proactive measures are taken to prevent adverse ecological effects before they occur. Resource preservation is another key aspect. Sustainable engineering actively works to protect finite natural resources for current and future generations. This extends beyond materials to include biodiversity, clean air, and fertile land, recognizing their intrinsic value and essential services. Finally, sustainable engineering plays a critical role in global climate action. By promoting renewable energy, reducing emissions, and sequestering carbon, it contributes directly to combating climate change. This engineering discipline is central to achieving a net zero future. Social equity stands as the second foundational pillar of sustainable engineering. It centers on designing projects that genuinely benefit the communities they serve. This involves understanding local needs and ensuring developments enhance, rather than detract from, community life. Promoting health and safety is a non-negotiable aspect of social sustainability. Engineering designs must prioritize the well-being of workers during construction and users during operation. Safe environments are fundamental to a high quality of life for all stakeholders. Considering the needs of all stakeholders is crucial, ensuring an inclusive and equitable development process. This involves engaging diverse groups, including marginalized communities, in decision-making. Their voices must be heard and their requirements addressed. Accessible design principles are woven into every project. This means creating environments that are usable by people of all abilities, including those with disabilities. Universal access ensures that public spaces and infrastructure genuinely serve everyone in society. Labor practices within sustainable engineering prioritize local talent and resources. This supports regional economies and provides employment opportunities for community members. It fosters a sense of ownership and investment in the project's success. Fair compensation is a critical component of ethical labor practices. Ensuring fair wages and safe working conditions uplifts workers and contributes to social justice. This commitment extends throughout the supply chain, promoting responsible business conduct. Ultimately, sustainable engineering aims to improve the quality of life for present and future generations. By creating healthy, safe, and equitable environments, it builds communities that thrive economically, socially, and culturally for decades to come. Economic viability constitutes the third indispensable pillar, ensuring projects are financially sustainable for long-term success. A project, no matter how environmentally sound or socially beneficial, cannot endure without a robust financial foundation. This requires careful planning and strategic investment. This pillar mandates a holistic consideration of the total cost of ownership. This extends beyond initial investment costs to encompass operational expenses, maintenance costs, and potential end-of-life considerations. A short-sighted focus on upfront cost can lead to greater long-term financial burdens. While initial investments in sustainable features might sometimes seem higher, this approach often leads to significant long-term savings. The upfront expenditure is often recouped through reduced operational costs and increased asset value over time. Sustainable choices prove to be financially prudent. For example, reduced energy consumption offers substantial cost savings over a project's lifespan. Investing in energy-efficient design and renewable energy sources dramatically lowers utility bills and operating expenses, providing a strong return on investment. This directly impacts profitability. Lower waste disposal fees also contribute to economic benefits. By minimizing waste generation and maximizing recycling, projects can significantly reduce expenses associated with landfill use and waste management. This streamlined approach benefits both the environment and the budget. Increased resource efficiency across all inputs translates directly into financial advantages. Optimized material use, water conservation, and energy management reduce the need for costly replacements and unnecessary expenditures. This lean approach enhances overall economic performance. Implementing sustainable engineering requires a truly multidisciplinary approach. It relies on the seamless collaboration across various fields, bringing together architects, urban planners, environmental scientists, and social scientists. This integrated perspective fosters innovative and comprehensive solutions. Key methodologies guide these efforts, particularly tools like Life Cycle Assessment, or LCA. LCA systematically evaluates the environmental impacts of a product or service throughout its entire lifespan, from raw material extraction to final disposal, often called cradle-to-grave analysis. This provides critical data for informed decision-making. The field also employs cutting-edge innovative technologies to achieve its goals. This includes the development and deployment of smart grids for efficient energy distribution, advanced green building materials with lower embodied energy, and sophisticated renewable energy systems. These technological advancements are pivotal. Sustainable engineering is far more than a passing trend. It is an undeniable necessity for our global future. The escalating environmental crises and growing social inequities demand a fundamental shift in how we design and build. This engineering paradigm offers a viable path forward. It represents a truly integrated approach, seamlessly weaving environmental protection, social justice, and economic prosperity into the fabric of every project. This holistic view acknowledges the interconnectedness of these factors, leading to more resilient and equitable outcomes. The ultimate vision is to create a more resilient and equitable future for all. Sustainable engineering actively shapes a world where human development coexists harmoniously with ecological health, ensuring prosperity and well-being across generations. This ambition drives its practitioners. Achieving this vision requires a fundamental shift in mindset within the engineering profession and beyond. It challenges engineers to broaden their perspective, move beyond conventional solutions, and embrace a deeper ethical responsibility to the planet and its people. This intellectual transformation is crucial. Embracing innovation is absolutely crucial for advancing sustainable engineering practices. New materials, technologies, and methodologies are constantly emerging, offering more effective ways to reduce impact and enhance performance. Engineers must remain at the forefront of these developments. Prioritizing the well-being of both people and the planet is the core ethical imperative. Every design decision, every material choice, and every operational strategy must reflect this profound commitment to a healthier, more just, and flourishing world. This moral compass guides the profession. Sustainable engineering offers a robust framework for addressing the increasingly complex environmental challenges confronting humanity. From climate change mitigation to resource depletion, its principles provide actionable strategies for creating a more stable and prosperous existence. It is our best hope for a viable future. Ultimately, the goal of sustainable engineering is to build a better, more sustainable world for everyone. It is an aspirational yet practical discipline, empowering engineers to be agents of positive change and architects of a truly thriving global society. This is the enduring legacy we strive to create.